Speaker for this session is myself, Saleem from the Centers for Disease Control in Atlanta, Georgia. There's a correction in the program. It's there challenges in HCV, HBV diagnostics, but Salas had asked me to prepare a presentation that's listed here, which is validation of in-house molecular biology methods, which essentially is PCR for the diagnosis of infectious diseases. So if we look at what are the general uses of any test that we use in the infectious disease arena, in addition to the diagnosis of a specific disease, these tests can be used for screening, for surveillance, for epidemiologic diseases, and also for evaluating whether the prevention strategies have worked. For example, if there's a vaccination campaign and you want to go back and see if this vaccination has worked, you use different assays for that purpose. Now, if we have to highlight what is the one single most important need for a diagnostic test, in very simple terms, this test is used for determining the presence or absence of infection. So if a test fulfills this function, I think that's the best test. And in order to meet this criteria, the test has to be accurate, very simple, timely, and affordable. If the test is too expensive, even if it's accurate, it's not of much use. So these are the broad criteria for a test that's used for identifying or differentiating presence or absence of infection. Now, the performance of a diagnostic test is dependent on various factors. For example, it depends on the characteristics of the population. What is the prevalence in a population? For example, I'll show you in the next slide. In the high-risk populations, the predictive value of a test is much higher than in a low-risk population. Host genetics plays a part in the performance of the test, and also the variability of the pathogen. For example, for HCV, we have 7 genotypes, and Anders Whittle told us this morning that he has identified an 8th genotype. So we all know the variability of the hepatitis viruses and other viruses, and when you design a molecular assay or a PCR assay, you have to factor in all those variabilities and design your reagents, primers, and probes in such a way that they will amplify all the relevant genotypes. And then, of course, the test methodology. If it's an automated platform, the chances of error are less. If it's manual, the chances of errors are there more. And the infrastructure and the resources of a lab also determine the performance of the test. Now, how do we evaluate the performance characteristics of a diagnostic test? Of course, one needs to have a gold standard or a reference standard that accurately will tell us whether a sample is true positive or a true negative. And this performance is measured by two very important parameters. One is sensitivity and specificity. Sensitivity in simpler terms means probability that a truly infected individual will test positive, and specificity is the probability that a truly uninfected individual will test negative. Now, what is the association of the positive predictive value with the prevalence of that particular infection? As you can see here, it's a very nice review. I recommend those of you who are in the lab to read this Nature Reviews article on the how to evaluate in-house assays. As you can see here, as the prevalence in a population increases or is higher, the positive predictive value of a test is also very high. In this case, for example, if you look at persons who inject drugs, and if the expected prevalence, for example, for HCV is about 20%, the positive predictive value of a test is more than 90%. In the low-risk populations, where the prevalence may be around 1%, the PPV is also lower. Now, the task that I was given is that how do we evaluate the lab-based assays? So if we look at the hepatitis C molecular assays, all these assays listed here, they have been approved by Food and Drug Administration or FDA in the United States. from different manufacturers here, and they have excellent limit of detection as low as 10 international units. So they're excellent assays. So if we have such a range of commercially available assays available, why do we need to develop lab-based assays? The reason that we need to have lab-based assays as well are here. Commercial assays are expensive. For example, a PCR test in the United States for HCV can cost up to $600 if you don't have insurance. At CDC, we get discounted prices. Even for us, it's like $200. On the other hand, if you have an in-house assay and you have your own primers, you have your own reagents, you can bring down the cost like 1/10 or 1/20. You can have a PCR test for as low as $10. These commercial assays, because they have built-in calibrators and controls and bar-coded reagents, so they have a shorter shelf life. And if you run out of one reagent, the entire kit has to be changed. So that makes them even more expensive. Also, commercial assays, since they have such a high limit of detection, they are so ultra sensitive, they also require larger sample volumes. Again, give an example of hepatitis C, the Roche assay requires about 0.5 ml of serum. And if you are dealing with a pediatric population, or if you have to test a sample for a number of markers, using about 0.5 ml of serum is too much. If you have in-house assays, for example, for HCV or HBV, we use 1/10 of the sample volume that's required by the commercial assays. And then again, you have to have specialized equipment. A Roche assay can only be used on the platform that's sold by Roche. An Abbott PCR assay can only be used on the Abbott MX platform. If you have your lab developed assays, you can use any of your PCR machines. You don't have to buy specialized equipment for that purpose. And also, these commercial assays, you cannot customize them. Let's say if you have a new genotype, or you want to design new primers or new reagents, they are closed systems. Your in-house assays do allow you that opportunity that you can customize or you can modify these assays. However, the big difference is that these commercially available assays or assays that have been approved either by FDA or a CE mark, they go through a very stringent process of approval. They have to test hundreds of samples from different populations before they get approval. So that's why there's a need that if we have a lab-based assay or an in-house assay, we need to verify and validate those assays before we use them for patient testing. Now, how do you do it? So there's a little bit confusion about what is validation and what is verification. On the top here are the definitions by WHO, ISO, FDA here. To me, they're very confusing definitions here. So I simplified it here. What's a validation? Validation is to determine that the test is repeatedly giving the expected results. That if you use this test on the same sample over a certain period of time, it will always give the same result. And what is verification? Verification simply means that the test performance characteristics are fully verified, that a true positive is really true positive in this test before the system's used for patient testing. Now, what methods should be validated or evaluated? So whenever you have a new method, it has to go through this process. If you are using a commercially available method and you make any changes in it, you need to go through this process. And if your quality control indicates that there's any change, you are not getting any expected results, so a validation or verification of the method is warranted. Now, how do we verify these lab developed tests? So these are the important parameters that have to be taken into account before a test is rolled out for patient testing. One has to measure the accuracy, precision, sensitivity, specificity, so on and so forth. I'll go through these items one by one. Now, before we go about designing a study for validation of the lab-based assays, you need to have well-characterized specimens. So these samples have to be tested by a gold standard, and these samples have to be in adequate volume. Now, For both verification and validation, you need to have a reference assay or a gold standard that has been proven to generate accurate results. And then you have to establish what's your acceptance criteria. What would you consider positive? What would you consider negative? And then you have to have a plan. How do you resolve a discrepancy? If your test sample is negative, the reference is positive, how do you resolve those discrepancies? And then we all know if we use a commercial assay, or if you have optimized an assay using serum samples, sometimes you have to test a stool sample for the same marker. For example, for hepatitis E, you can detect HEV RNA in both serum and stool samples. So if your method is developed for testing serum and now you are using it for stool sample, you need to validate the method for that type of sample material as well. Sometimes you have tissue samples, you can liver tissue or other tissue, and you want to detect whether your viral nucleic acids are present in that tissue. So again, before you apply a method that has been used for serum or stool or other samples, you have to again validate it for that type of sample material. Now, what's accuracy or trueness? The definition of accuracy is how close is the result to that determined by the reference method. So if you have the gold standard or the reference method calls a sample positive, your in-house assay has to call it positive as well. So if it's also positive there, that means your test is accurate. Now, how do you determine the accuracy of the test? It's very simple. You just do a comparison of the methods. You compare the results from the reference method with your in-house method. And then you have to have, again, as I mentioned earlier, you have to have thoroughly characterized samples. And what those samples could be, one can use for this residual patient samples. What we recommend always, I think maybe WHO also has the similar recommendations. If you have patient samples in your lab, you have tested them, you know which samples are positive, negative, you have enough volumes, you just store them, you archive them appropriately at -20 or -70. You can use those samples for measurement of the accuracy of your assays. And you have to have a decent number of both positive and negative samples. So one of the questions people ask, what's the number of samples that should be used for this purpose? So it's always the larger the sample size, the better is. But the minimum recommendation is use at least 40 to 50 samples, and below 20 is almost is always unacceptable for this purpose. So what is the analytical sensitivity of an assay? The analytical sensitivity is the ability of the assay to detect the lowest concentration of that particular analyte. As I showed earlier in one of the slides, for example, for HCV PCRs, those commercial assays can detect as low as 10 international units. So that's the analytical sensitivity of those assays. What's the lowest limit of that analyte that can be detected? So you have both qualitative and quantitative assays. In qualitative assays, you only have a positive or a negative. You do not have the numerical value. So in quantitative assays, you measure your sensitivity by the limit of detection. What's the lowest limit of the titer of that nucleic acids that can be detected by your assay? And how do you measure the analytical sensitivity? Generally, you have established standards. WHO has standards for, I think, a number of pathogens. We have standards for all hepatitis viruses, A through E, so that can be used. You know the exact titer of those standards. Or in certain cases when you do not have a standard, so you use serial dilutions of a known positive sample. So you determine the limit of detection of your assay by doing serial dilutions of a sample that you know is positive. So what is the diagnostic sensitivity? In simpler terms, diagnostic sensitivity is that a truly infected individual will test positive. It's as simple as that. And you use this term positive predictive value is the probability that those testing positive by the test are truly infected. As I showed earlier in one of the slides, this positive predictive value depends on the prevalence of that infection in the population. What is analytical specificity. Analytical specificity is the ability of an assay to detect only the intended target. So if you are looking for HBV DNA in a sample and your primers, probes, reagents should only amplify HBV sequences. You should not be able to amplify unrelated sequences. So in checking the analytical specificity, sometimes there are substances that can interfere with your test, and those are listed here. If a sample is hemolyzed, or if it is icteric or lipemic, they can interfere with your results. So you need to make sure that your sample does not contain all those interfering substances. And the way to check this specificity is that they always run a panel. You include in your evaluation panel samples that have all these characteristics, and you find out that these are not interfering with the performance of your assay. And again, what's the diagnostic specificity? Is the probability that a truly uninfected individual will test negative, that you don't have any false positives. That's the diagnostic specificity. Now, another term that we use in the assay evaluation is the precision. Precision is how well a result can be reproduced when a test is applied repeatedly to the same sample. And how do you measure precision? Precision can be measured when you test the same sample in different runs. It can be done on the same day. You can have the same sample on the same plate or in the same run at multiple times. You can test the sample 15 times, 20 times in the same run. Place it in different locations, and then you find out, can you get the same results. Then you can run the same sample on different days. That's run to run variation. And also you also measure precision, that you give this sample to different people, different technicians in your lab, and you have the same sample tested, and you find out that every technician gets the same result. So if there is no difference from run to run, intra-run, inter-run, from inter-operator variability, that means your test has a very good precision. And for this purpose, the types of samples that can use is generally standards, or there are commercially available quality control material. There are also proficiency samples available, commercially available, and one can also use well-characterized patient specimens for this purpose. Now, what's a reportable range? Reportable range or linear range of an assay is what's the range of the assay that the assay can detect those nucleic acids and those targets. It does not apply to qualitative assays because the results there are positive or negative. But for quantitative assays, it is the spread of those results under which the assay can detect those nucleic acids. For example, the Roche HCV assay has a linear range from 10 international units to 20 million international units. So if a certain sample has viral RNA titers that are above 20 million international units, so this is beyond the linear range or the reportable range of the assay. So what you need to do then is sometimes you need to dilute the sample to bring it down to the linear range. Similarly, you may have seen that all those commercially available assays, if the value in a certain sample is below the linear range, they say less than 10 international units. So they don't call it negative, or they don't have a number that they can assign. So the result is reported as less than whatever is the lowest limit of detection. So that's the reportable range of the assay. Now, what's a normal range or a reference interval? It's a range of values that's typically found in an individual who does not have the disease. This does not apply to the molecular assays. For molecular assays, it's positive or negative. If someone is infected with hepatitis C, has current infection, the individual would be HCV RNA positive. If the person is not infected, will be HCV RNA negative. This reference range is mostly for other markers. Now, I think so. A little bit about the controls that you have to use in your assays. A number of controls that have to be used whenever you use your lab developed assays. So commercially available assays they have their internal controls, they provide controls with the kit. But when you have your own assays, you need to have well-defined positive controls and negative controls. So what are the characteristics of positive controls? So you have to know that these are from clinical cases. You have to have an association with the clinical illness of the patient. They have to be tested positive by the reference assay, by the gold standard assay, and these could be the positive control samples could be patient samples. Sometimes, let's say we are dealing with Zika now, or you're dealing with Ebola, you do not have a large panel of samples, or your SARS came about, so you did not have well characterized samples. So under those situations, positive control could be just a clone. You can use an amplicon that you have amplified and use that as a control. And of course, patient specimens, they serve as excellent positive controls. And in certain cases, you can use even tissue culture material as a positive control samples. And again, the positive control in a certain assay has to match the sample that you're testing. So if you are testing serum samples, your positive control should be a serum sample. If you have developed an assay for stool samples, and you have to have a positive control that's a stool sample. So the negative controls, essentially in a molecular assay, use a negative control to detect contamination, that you do not have false positives. So a negative control could be just water, a buffer, a normal human serum. But an ideal negative control in a molecular assay is a sample that contains an unrelated target, which is, let's say you have developed an assay for HCV RNA. Your ideal negative control would be that you include a sample that's positive for HAV RNA. It's unrelated, it's positive for an unrelated pathogen, and it's an ideal negative control. It's not always possible, but that's an ideal situation. And when you test, include your negative and positive controls, where do you place them? There's another question lab people say, well, I used my negative control. So they use this negative control in the beginning of their assay when they are clean, they keep it separate. That's not the way to check your system. So the negative control has to be at the end of the run. So when you use your pipetters, when you have tubes on your in front of you on the bench, so it has to be at the end of the run. And if you are testing large batches of samples, you need to have multiple negative controls. That means, let's say if you have 100 samples to test, there should be a negative control or a negative sample after every 10 tubes or after every 20 tubes. You just cannot have one negative sample in the beginning and say, well, I did not have any false positive results. That's to check the contamination. Now, this is my summary slide here. Looks complicated. So this summarizes how do you do this validation and verification. Essentially, it's a 3-stage process. In stage 1, which is the most crucial one, which is about planning and development, it's this stage where you want to determine all the characteristics of your assay. What's your intended target? What is your limit of detection of the assay? How many samples you want to include? How do you resolve discrepancies? So I think in any assay validation or verification, this is the most crucial step where the lab supervisor, the clinician, even the policymakers have to get together, have to set aside resources for this particular purpose. How do we go about validating and evaluating an assay? Then the second step is the testing and analysis. So once all the parameters have been laid out, then the testing starts. And again, as you can see here, in the first phase, if you have a well-characterized reference assay, in this case we have shown here, if you have an FDA cleared test system, your job is much better. But in several situations, you do not have an approved assay. So you have to go through all the different elements that are listed here. And the second stage is you perform the actual testing, and if everything goes well, then you go to the third stage, which is reporting and implementation. So if you get all expected results, you are ready to roll out the assay for testing actual patient samples. And with that, I thank you for your attention, and I'll take any questions.